So today we finally get to see something a little more interesting. And by interesting, I mean instead of looking at functions of one variable or two variable or three variables that spit out real numbers, we get to see functions, well, we'll start with just functions of one variable, but that actually spit out vectors. So these are sometimes called vector functions. So these don't eat vectors, unless you think of numbers as kind of one-dimensional vectors. So they're not eating vectors, but they spit out vectors. And so we're going to go through those as quickly as possible. And if we get through that all today, we'll start looking at vector fields. And when you see this word field, those of you who are in Math 267, I don't want you to be confused. This is not an algebraic field. It doesn't mean a set with two binary operations, right? And where under the multiplication operation you have inverses. No, that's not what we mean here. Here we mean fields in the sense of gravitational fields, right? Electrical fields, that kind of field. And in fact, all of those are going to be examples of vector fields. All right, a vector field is just going to be a function that eats vectors and spits out vectors. Okay, so we'll see if we get there. But we'll start with vector functions. So I'm going to introduce a little bit of notation which is highly non-standard, but which I think is useful. And maybe somebody will find it useful enough to make it standard. All right, so a vector function is a function, we'll call it, about, what do I like to use? When I used R. I'm going to use a vector line over it to remind you this is a vector function, but it's not a vector itself. It's a function. And what does it eat? It's only right to say R of t. It eats a real number, and it spits out a vector. And that vector should have a certain number of variables in it, or a certain number of components. So maybe it has n components. Okay, so it could be a vector in 2 dimensions, 3 dimensions, 5 dimensions, n dimensions. See, all right. Hello?
Hey.
Who are you? Some hair's cut.
Yeah.
Okay. Now, this, as I've written it, isn't really correct. And it's very subtle. Why is this not correct? If my output is supposed to be vectors. Well, Rn, these are n tuples. Right? Now, if you have an n tuple, you can associate to it a vector that goes from the origin to that tuple, right? If you have a 2, 4, you have the vector that goes from 0, 0 to 2, 4. Right? So for every point in R2, you can associate a vector that goes from the origin to that point. But we know that we can take that vector and move it all over the place. Right? And the endpoint of the vector, if we move it, would be different than 2, 4. But we still treat it as the same vector that went from the origin to 2, 4. So this is misleading notation. So to not mislead you, I'm going to put a vector sign over it to mean these are the vectors. I don't treat the points as just points. I'm really treating each point as the vector from the origin to that point. But of course, everything in here is going to look the same to us. Okay, so this is what a vector function is. So for instance, you might have a vector function on R3. And what does it have to look like? Well, it has to give you vectors in R3. And we know that every vector in R3 looks like something times I plus something times j plus something times k. And so this R of t can actually be broken up. It can look like something times I plus something times j plus something times k. So this is a function of t. So this f, g, and h, these are actually functions that, well, they eat real numbers, but actually spit out real numbers, because these should just be coefficients. They should be real coefficients. You look really weird right now. What's going on?
Oh, I don't have my book. Ben have it.
You can't take notes right now. We'll give her notebook back. We can make photocopies of the... Maybe you look so strange. That was the weirdest look you've ever given me. Okay. So do you get what I'm doing when I write it like this? You can write down functions, right? Every R of t looks like something I plus something j plus something k. The image should be a vector in R3. And so you get these functions, f, g, and h, and these are called component functions. So whenever you have a vector function on Rn, you're going to get n component functions. If it's R3, you get 3 component functions. So those of you who've worked a little bit with parametric equations, this is really just, I don't know, this is somehow an equivalent way of writing parametric equations, but in a more condensed form. So let me give you an example of that. So let's say you write down the following parametric equations. X equals cosine of t, y equals sine of t, and z equals t, where here t is allowed to run through all real numbers. So graphically, what's going on? Well, if you forget the z equals t business, that's basically if you just project onto the xy plane, what is this graph going to be? X equals cosine, y equals sine. Those of you in complex analysis have an unfair advantage here. Yeah, it's the circle, right? The x, if you look at the cosine of t on the unit circle and the sine of t on the unit circle, they're actually representing the x coordinate. Okay, we did theta, sine of theta. Cosine represents the x coordinate, the sine represents the y coordinate. So actually this is giving you a circle. Okay, so if you just project it on the xy plane, you get a circle, but then you have the z equals t business. And what does that do? Well, as t increases, that means it's going up. So the z is going up. So what is this graph going to look like? Well, let's see. At t equals 0, it should give you 1, 0, 0. So it would be out here. And then it's going to start to go in a circle. But the z is increasing, so it's not... Do you see what it... Well, that's a little too much, and those are getting smaller. What's it doing? Right? It's staircasing around. Right? It's going in a circle, but the z is increasing, so it's spiraling up. Right? But it's still going in a circle. And then, of course, it keeps going down. It's not really intersecting itself. I just can't draw. It's really going down, right? Down, 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 up, up, up. Okay, so this is a parametric thing. But we could actually view this as a vector function. So as a vector function, you get r of t equals cosine of ti plus sine of t j plus t k. So you can just put it into one equation. So really, of course, if you take any parametric set of parametric equations here, you can turn it into a vector function using this as a model. And if you start with a vector function, you can say, okay, let x equal this, let y equal that, let z equal this, right? Or x is the first component function, y is the second component function, z is the third component function. And you'll get a set of parametric equations. So somehow vector functions are just another way of talking about parametric equations. But this interpretation is going to make things a lot easier to write down. So for instance, well, what's our pattern always? You start off by defining functions. And then in calculus, what's the first thing you do with those functions? What's that?
Derive.
You're talking about derivatives, right? Before you do derivatives, you have to talk about continuity. Before you talk about continuity, you have to talk about limits. Okay? That's, of course, where calculus really begins, is talking about limits. Okay. When we did functions of one variable, of course, that was 165. That's what we did. When we started this course, we did functions of 2 variables or 3 variables or more. That's what we did. We wrote down limits, then continuity, then differentiation, then integration. Okay, cool. The pattern works. Let's try it. What should the limits be? So let's say I want to do the limit as t goes to a of a vector function, r of t. Well, there's a kind of an obvious thing to do. So remember, our limit is of r of t, and r of t we know we can always write in terms of its component functions. So what would be a natural thing to do when you're taking the limit as t goes to a of r of t, given this interpretation of r of t? How would you compute that limit? Knowing that over here you have functions of one variable, and you know very well what to do with those when it comes to limits. Yes, take the limit of each of these, right? So you might say this is... I'm going to run out of room, so let's write it here. This is the limit as t goes to a of f of t, I, plus the limit as t goes to a of g of t, j, plus the limit as t goes to a of h of t times k. And these limits are separate from the j's, from the i's and k's. So here, these are the component functions. And it turns out this is exactly the right definition. While we're here, I may not always want to write my r of t in this form with the I, j, and k. So I sometimes will write it in vector form. And when I do that, an alternative form here is going to be to write it as f of t, comma, g of t, comma, h of t. Okay. This means the same thing. Okay. And so my limit would then, well, I won't write it. You could translate it. Just replace all these i's, j's, and k's with commas, put parentheses around, get rid of the pluses. Okay, so if that's your definition of limit, what's your definition of continuity? When is a vector function continuous at a point? So, R of t is continuous at say t equals a if, okay, what's the definition of continuity? What's that?
You won't have one that's jumping.
It's not jumping, but there's a precise, what does it really mean?
Getting close and staying close.
What's that?
Getting close and staying close.
So we're talking about limit is getting close and staying close, but continuity is a very precise definition. And it's very short too. A function is continuous at a point if the limit of that function at that point exists and it equals the value of the function. So first the limit should exist, so it shouldn't go off to infinity or just the function doesn't it goes like this really close to 0 or something and never converges, whatever. But then also what Kaiwei said, it shouldn't jump away. Like here you have a function that looks like this, the limit exists, right? It's that point in the middle, but at that point it might jump up. Even though the limits both agree, it might jump up. And we don't want that to happen. We want the value of the function at that limiting point to be the limit point. So f is continuous if the limit as t goes to a of r of t equals r of a. Okay. This is, if you replace r of t with f of x, this is exactly the continuity condition we had for single functions of one variable. Okay, so you have limits, you have continuity, and all of the normal properties of limits and continuity exist. By the way, I didn't say that here, but here I'm assuming all these limits exist, right? If these limits don't exist, then this limit doesn't exist. So what I should say is if all the limits exist. And that's always going to be the case, right? So if you have a limit of a sum, it equals the sum of the limits, if all the limits exist. The limit of a product is the product of the limits, if all the limits exist. Yeah. Continuity. Two functions are continuous. Then their sum is continuous. Their product is continuous. Subtract, divide, as long as the bottom isn't 0. Right? All the normal properties of continuity are going to hold. Okay, so once you get limits and then you get continuity, then you're ready to define the derivative. Exactly. Okay, so you got limits, you got continuity, define the derivative. Okay, so what should be the definition of the derivative of a vector function? What's the definition of the derivative of a regular function? The limit as h approaches 0 r t plus h minus r of t divided by h. Okay, and that's going to be our definition. It's exactly the definition that you want. Yeah. All the properties of derivatives hold right. And of course, this is if the limit exists. It might not. What you might like to hold actually does hold. So you have this r of t, and you want to compute its derivative, which means you have to compute this limit, right? But come on. When's the last time I made you actually compute a limit to take a derivative? Okay. So if I don't want you to take a limit to compute the derivative, how do I want you to compute the derivative of r of t? What's that? Well, if this was integration, I'd say let's prove the fundamental theorem of calculus again. But this isn't integration, it's differentiation. It should be easier. Differentiation is always easier, right? So Well, this R of t, oh yeah, I always have that way of writing it down in terms of the component functions. R of t is f of t, g of t, h of t. So, what would you like to have happen? That the derivative of r is what? Yeah, you just take the derivative of the components. That's exactly what happens. So we have R of t equals f of t, g of t, h of t is a vector function. Let's say a differentiable vector function. Then the derivative of r is just the derivative of f, comma, the derivative of g, comma, the derivative of t, of h. So it's exactly what you want. So it's really easy. This could not get any easier. Good. Okay. So let me write down some of the rules for differentiation. And these rules you're going to prove on the homework. I won't prove them here. So the first one, well, okay, let me set it up. Let me give you, so let's let u of t and v of t be differentiable vector functions. And f of t should be a differentiable real value function. Okay, so f is not a vector function, it's just a regular old function which has a derivative. And then let me take just a constant. I'm going to need a constant c. Okay. And for the purposes of these formulas, which will get boring if I always have to write down of t, we know everything is of t. So I'm just going to write u equals u of t, v equals v of t, f equals f of t, and so forth. Except in the very last one where I can't do that. But for the most part, that's what I'll do. Okay. So the first one is what happens if you add two vector functions and take their derivatives. So let me be clear. These are not vectors. Right? U and v, these are vector functions. And you can't take the derivative of a vector. What should this be? Sum of the derivatives. Derivative of sum is the sum of the derivatives. Any guess what the next one's going to be?
C.
Linearity, right? This is the linear transformation. Okay. If you multiply a vector function by a constant and take the derivative, this is the same as taking the derivative and then multiplying by the constant. Okay, done. Okay, now there's something a little more interesting. Let's say I don't put down a constant here, but I put down a real function, namely f. Okay, so when I write fu, it's unfortunate. I mean f of t times u of t. So they both eat t. This spits out a number. This spits out a vector. So I get a constant times a vector in the end. So the answer is a vector. Still. Okay, but if I multiply these together and take the derivative, it's not just this isn't a constant. You can't just pull it out. You actually have to use the product rule. Even though this is a single variable function and this is a vector function. By the way, these f's are sometimes going to be called scalar functions now. In any case, you still can use basically the form of the product rule. And this works whether or not...
Are you missing something?
What? Oh, sorry. Thank you. And this works actually even if f is a vector function itself. So if you have, that's not a dot product. If you have two vector functions and you multiply them and you take the derivative, then this is u prime v plus u prime.
When you say multiply them, it's dots, cross, or just...
Yeah, so actually, no, I put it there, but I erased it. What I mean here is the dot product. That's a perfect question. If I don't put anything here, what does it even mean? I might say, oh, well, I mean, do u of t times v of t. But those are vectors, and we don't know how to multiply vectors together. You have to use one of these products that we have, a dot product or a cross product. So here I'm doing the dot product. Okay, but this begs the question. What if I didn't put the dot product? What if I put cross product? And it turns out that it's exactly the same, only, so here they should all be dot products. You just copy the same formula, but with cross products. And the answer again, this answer is a vector. Okay, any more? Oh yeah, right. So then the last one is the chain rule. So what if you have u of f of t? So u is a vector function, but it actually can eat this single variable function first. And the answer is, well, you do it just like you do the chain rule normally. You take the derivative of the inside times the derivative of the outside, evaluated at the inside. So, have fun proving those. Enjoy. Of course, you can use that all these properties hold for regular single-valued functions. Scalar functions. So you know, for instance, if you had f plus g prime, that for just regular functions, f and g, that the derivative of that is additive. You know that already. So you can use that. And you can use this theorem. It says that the derivative is given by just taking the derivative of the components, which is going to allow you to reduce questions to the original problem. Okay, so now you know how to differentiate those suckers. I would show you an example, but I think it's probably clear by that theorem what you would be doing. I would give you a function, and then you'd say, well, let's see, there's 3 different things to differentiate, and then you differentiate them because you know how to differentiate. That would be that. So okay, once you get derivatives down, what's the next thing you do? Integrate. Okay. So how should we interpret that? Well, there's a sort of an obvious interpretation if, again, you go back to the component functions. Just write this as the integral from a to b f of t, comma, the integral from a to b g g of t, comma, the integral from a to b, h of t. Of course, mind you, when I've done this, I've done this for vector functions that go into R3. There's nothing special about 3, right? Other than this cross product formula. All these things are holding for Rn, right? For vector function in any. And the same thing would work here. There were 4 of them or 2 of them. Okay, so that's how you integrate. That's not so bad. All the properties of integration should hold. If you write, well, let's say that f of t, g of t, and h of t are antiderivatives. For f, g, and h, respectively. Respectively here, in case you don't know how this expression is used, means f of t is the antiderivative for f, g of t is the antiderivative for g, and h of t is the antiderivative for h. Okay, so if those are not the antiderivatives, but they are antiderivatives, then, well, we know that we can use the fundamental theorem of calculus to write this as big F of b minus big F of a. And so forth for the others. So the integral from a to b of r of t dt equals big F of b minus big F of a, comma, big G of b minus big G of a, comma, big H of b minus big H of a. So it makes sense to let big R of t equal big F of t, comma, big G of t, comma, big H of t. So that the integral from a to b of R of t dt equals R of t evaluated at b and a. So basically the fundamental theorem of calculus holds. You can find an antiderivative for R by just finding antiderivatives for all the component functions. Of course, this assumes that all the component functions have an antiderivative. Okay. But if they're continuous, then we can do all these things. Well, at least we can compute these. Okay, any questions? Yeah? Okay, those are vector functions. You might wonder why. Why do we even care? Well, of course, there are kind of obvious examples of a vector function. Imagine, well, here's kind of a silly one. Imagine you have a specific point in the room. And you're tracking airflow at that point over time. So t is going to represent time. At any given time, you can ask, what's the airflow from that point? And there's a vector. Okay? So you now have a vector function. It eats time, and it spits out the vector at that point in time. Now, the reason why I said this is kind of a stupid example is because we usually don't care about just one point. We usually care about the whole room, or maybe the whole world, when we're caring about airflow. Okay? And that, of course, is why we want to talk about vector fields, which eat vectors. Right? They can eat points in space and spit out a vector. Okay. But in the process of talking about vector fields, it's going to be important that we have the language of vector functions sitting around. Okay. And they're terribly easy, so it only takes a few minutes to really write down all their properties. Yeah? Okay. Okay, so any questions before we start this? Vector fields. This is the big time now, right? This is where things get really cool. This is where the physicists who aren't in the room would start to salivate if they were. Okay, so just so we set our terminology, scalar functions are going to be anything that spits out a single variable. So it's f. It can eat several variables, but it's going to spit out one number. So all of the functions that we've excuse me, all the functions that we've played with so far have been scalar functions. These are somewhat trivial. Yeah? The course has been trivial up to this point. They're also called scalar fields. Just in case I accidentally say that word. Okay, and then we just defined vector functions. Okay, and these are these R of t's, right, that eat real numbers and spit out vectors in Rn. Now, the next thing is going to be vector fields. And for the purposes of this course, I'm going to restrict the definition and just say a vector field, I think I use capitals, probably use an F or something, is going to eat a real point in Rn, and it's going to spit out a vector in Rn. So I'm going to keep n the same in both of these. For all of our purposes, this is just exactly what we need. I'm writing f of t, that's silly. It eats not just a t, it eats a tuple. Okay, so that's what we're interested in now. Now, just like with vector functions, which spit out vectors and give you then component functions, because f is spitting out vectors, you get component functions. So for instance, we're going to be very interested in vector fields when n equals 3. So say you have some f of x, y, z, so it eats a point x, y, z, then you can write the image as, well, there should be 3 functions, and I'm going to call them p, x, p, q, and r. So it will be p plus q times j plus r. So it's x, y, z times k. Okay, and again, these are called component functions. And these are scalar functions. Right? They may eat something in R3, but they're definitely spitting out numbers. Right? Because these are supposed to be vectors in Rn, so it should be a constant times I, a constant times j, a constant times k. So these are scalar functions. Okay, so take a guess. What's the first thing that we care about? Limits. What will be the second thing we care about? Continuity. Good. Okay. Last time we saw that you picked up the limits and the continuity by looking at what? How did you, if you just had a vector function, r of t, equal to, say, f comma g comma h, how did you test if R had a limit at a point? You looked at the component functions. How did you test whether it was continuous at a point? Well, let's see, you had that formula. You looked at the limit of the function at a point, and you said that actually has to equal the value. But of course, the limit is checked by looking at the component function, and the value can be determined by looking at the component function. So actually, continuity implies it's continuous at all the component functions. Now, does the component functions are continuous at that point? So, for vector functions, limit and continuity are inherited from the component functions. And the exact same thing is going to hold here. The way we test limits, continuity, is by just asking, do the limits exist for the component functions? Are the component functions continuous at that point? So there's no change. So limits and continuity of vector fields are inherited from their component functions. Everybody understand what I mean by that? If you want to check if a vector field F is continuous at a point, you just check whether P, Q, and R are continuous at that point. If you want to check what the limit is at a point, you just check the limit of P, Q, and R. Okay. Oh, that's 5 minutes fast. Okay. Okay, so what's an example of a vector field? Well, of course, you have some physical ones that we'll come back to, the gravitational field, right? So if you pick a point in space, there's gravity, right? The Earth is pulling it, and that gives you a vector in R3, right? You can draw a little point, right? And of course, what happens? The farther away you are from, say, the center of the planet, say from the Earth, what happens to those vectors? Well, let's see. They're always pointed where? Where's gravity pointed? Where am I being pulled towards? I'm pulled down, right? But down towards what? The center of the Earth, okay? So if you pretend that I'm not a person, but a point. Yeah? Okay. On a macroscopic scale, this makes sense. Yeah? Okay, so on this point, if you took the vector that emanates, for this point, you'd say, okay, there's a vector pointed towards the center of the Earth. Now, how long is that vector? Well, what does it mean, the length? What does the length signify? Well, remember that vector isn't actually going from me all the way to the middle of the Earth. That vector is just a little vector, points like, it's about that far. Yeah? What is that signifying? If I made that vector longer or shorter, what could that signify?
The force.
It's the force, right? It's the amount of the force. It's the magnitude of the force. So it's the magnitude of the gravitational force. So it's how hard gravity is pulling on me. Now, does gravity pull on me the same no matter where I am? No. Where does it become different? If you're, say, in the mountains, so it's a little higher, right? Then gravity pulls a little less. If you're up in space, right? Say you're at the International Space Station. Is gravity the same? No, absolutely not, right? It pulls less on you, right? The farther you are away from the body being the Earth, the less gravity is pulling on you. So we'll come back to there's a formula from physics that describes it. Newton figured this out. Okay, so this is a nice example of gravitational, the field, right? This is a gravitational field. There's electrical fields. Right? There's fields that you get from, say, water passing through something. There's flow, right? The flow of a gas or a liquid. Okay, but there's actually a field that we've already used in class. Okay? And that's the gradient vector field. So remember, let's say you had a function f, a scalar function, just on R2, to make it easy. we defined delta f of x comma y as, well, as the partial derivative of f with respect to x at x comma y, comma the partial derivative of with respect to y of x comma y. So we're actually spitting out a vector here. So that means that delta f, or delta, I almost got caught there, nabla f, or gradient of f, is a vector field. This eats a point in R2, and it spits out a vector in R2. So this is a vector field. And it's called the gradient vector field. Surprisingly, because there's a gradient. Okay. Let me just finish one more thing. Of course, this would work if I had a 3 instead of a 2. Right? We can define the gradient for three-dimensional scalar functions. That's fine. It's going to turn out that there's a lot of vector fields that are, in fact, gradient vector fields. And these turn out to be important. So important that we give them a name. So, just finish with a definition here. A vector field F is called, and this name is not something a mathematician would have come up with. It's definitely, you can guess who came up with it. It's called conservative. If the vector field favors low taxes and small government. Now, if there exists a scalar function f such that the vector field f equals the gradient vector field of f. When I wrote here called the gradient vector field, I can write of f. So if your vector field is the gradient of some function, then you call it a conservative vector field. It's also a gradient vector field, but it's called conservative. So one of our first questions is going to be, how can you detect when a vector field is conservative? Okay, so we'll pick up on that tomorrow.